Morning, nerds. She knows me well. Welcome back to Precalculus, I think. Yes, this is Precalculus. Finishing up section 1.4 that we started before the storm chased us out of school for a couple days. And in the first half of the notes, we talked about composing functions and restricting their domains. And finding domains of things is, like I said, probably going to be the most challenging concept on your upcoming tests. Then we decomposed functions, took them apart, and lastly, applied them to the real world in figuring out how to make compositions work for us. We now shift gears, even though it is in the same section, and go to some slightly different stuff. We'll start by talking about a relation in mathematics. What is a relation? A relation is any equation that relates x's and y's. The ones that we're really familiar with are functions, where for a function, you plug in an x and a y comes out. And for every x, there's exactly one y. That's a very special kind of relation. Here we have x squared y, and it's actually kind of hard to see, x squared y plus y squared equals 5. The first thing we're supposed to do is determine which of these three coordinates actually exist on this relation. And then from there, we'll talk about whether or not it is a function. And the way we confirm that a point is or is not part of a relation is literally just plug it in to x and y. And if you get a true statement, yay, click your heels, that coordinate is on the graph of the relation. So we're just going to plug them in. So we're going to take 2 comma negative 5, and we're going to throw it into here. And let's see, we get 2 squared times negative 5, and then plus negative 5 squared. And we're curious, so that's why I'm putting a question mark there. Does that equal 5? If we get a true statement, that's part of the relation. If we don't get a true statement, that's not part of the relation. 2 squared is 4. Negative 5 squared is positive 25. And 4 times negative 5 is negative 20. So yes, negative 20 plus 25 does equal 5. Chitty chitty bang bang. That is part of the relation. Yay! If we graphed it, we would find 2 comma negative 5 on that graph. That's what that means. Next, we'll try 1 comma 3. We'll see if 1 comma 3 is part of the graph. 1 squared times 3 plus 3 squared. We're curious, is that 5? Well, hopefully it's obvious that it's not, because 3 squared is 9, and all of this is going to be positive. 3 plus 9 does not equal 5. So no. The coordinate 1 comma 3 would not be found on the graph of this relation. And then we'll try the last one. Switch over to purple. 2 comma 1. 2 squared times 1 plus 1 squared. Curious, does that equal 5? Well, 2 squared times 1 is 4. And 1 squared is 1. So yay! We found another coordinate that is on the relation. Well, on the graph of the relation, I should say. So why bother with any of this? The reason why is because I want to know, is this relation a function? And how would you know? What's that? Well, not just if the x's are all different. There's a little bit more to it than that. Now, if you can guarantee that every x only happens one time, then yes, that's one way of knowing, but that's not a way of saying not a function. So it's a one-way street. But with the information I have right now, I do have enough information to claim function or not. Yes?
Is it not a function because different values are giving the same, different x values are giving the same y value? Sorry, different inputs are giving you the same output?
You're close. It's because you said it backwards. Because one x is giving me 2 different y's. You switch the words inputs and outputs. So right here we have x equals 2. If this is our calculator, you did some math with the number 2, and it gave you the result of -5. And then the next time you use that math with 2, it gave you the result of 1. Your calculator's broken. It's clearly not functioning correctly. So because one input, or x value, gives two different outputs, or y values, this is not a function. Literally, if you were going to plot some points, if you were going to plot some points at x equals 2, you would have a dot at 2, 5, and then directly below it, -5, excuse me, directly above it, you'd have a dot at 2, 1. So Noah, what are you trying to tell me about that then? It would fail the vertical line test because the straight line would hit it twice. Yep. In fact, if you were super curious to know what it looks like, it's not going to work on the camera. Yeah, sorry, I said not a function. Let me do some quick math on my graphing calculator since I can't put this image of Desmos on the screen. Okay, anyway, like I was saying, I can't get Desmos on the screen, well, at least not for the video. That is what the graph of this relation looks like. And you don't have to know that. And I didn't know that until I graphed it on Desmos. And you'll notice, I hope, that this graph is two different colors. And that's because the graphing calculator can't graph this as one equation. I had to do a little bit of mathematics and turn it into two equations because the graphing calculator in function mode, which is the mode it's currently in, can't graph something that's not a function. But the blue thing itself was a function, and the red thing itself was a function, and it was actually possible to separate this into two different functions. The process of taking a relation that's not a function, but breaking it into multiple functions is called implicitly defining a function. Nice segue, right? Sometimes we have things that are not functions, like this circle, x squared plus y squared equals 4. This is the circle centered at 0, 0 with a radius of 2. We have the ability to solve for y. So you subtract x squared from both sides, then you take the square root of both sides, and what you have to remember from your algebra days is that when you cancel a square with a square root, it's going to create a plus or a minus. So this one relation can be defined implicitly as two separate functions, the positive version of the square root of that graph and the negative version of the square root of that graph. And if you put these two on the same graph, they'd be a circle. The calculator would do its best. Honestly, the graphing calculator would fail right at the x-axis and it would show you a hole in the graph, but that's only because of the way it colors pixels. It's not because the calculator did anything wrong. But yeah, when you can solve for y and generate more than one equation that are functions, that's called implicitly defining a relation. And that's how I managed to get this onto my graphing calculator. An involved math that I don't expect you to be able to reproduce, but you have the skill set technically. I used completing the square, if you remember that terminology. I took the relation, I rewrote it so that it said y squared plus x squared y equals 5. I then completed the square, treating this x squared as a number. So I pretended this was a number and I tried to complete the square for this quadratic, giving me this x to the 4th over 4 term. But I can't just create something on the left, I had to do it on the right also. I called 5 20 over 4. I combined it to one fraction. This is a perfect square trinomial that factors to one set of parentheses squared. That's what it means to be a perfect square trinomial. I then took the square root of both sides. That created this plus or minus. Square root of 4 is 2. I subtracted x squared over 2 from both sides. And then because they had the same denominator, I wrote it as these two functions. And there they are. And I had no way of knowing what that was going to look like until I put it on Desmos. And all of that work is not always possible. It is not always possible to isolate the y values. But when you can, it's called implicitly defining a relation. And you guys will practice isolating y values. Here's the good news. This example in the notes right here is harder than anything I'm going to throw at you in the homework or on a test. This example involves something I just talked about on that sheet of all that nerd stuff I did. So we are going to describe what this graph looks like without graphing it. And by the way, your calculator can't do it the way it sits. You'd have to do it on Desmos. Or you'd have to be able to isolate your y values. The issue with isolating the y values right now is that you have y squared and you have y. That guarantees some kind of quadratic is going on. And because I have y squared and y's, you're either going to have to hate your life and complete the square like I just did, or recognize that this is a very special thing. A thing that's in the format a squared plus 2ab plus b squared. That's what you're looking at right here. Square in the front, square in the back, and double the product of the square roots in the middle. This is a perfect square trinomial. And you would have seen these in Algebra 1 and again in Algebra 2. This setup factors instantly to a plus b quantity squared. That's a formula that you should have seen in Algebra 1 and Algebra 2. Now, like I said, that is more challenging than what I'm going to ask you to do in the work at home and on the tests. So we can factor x squared plus 2xy plus y squared. It factors instantly to x plus y quantity squared equals 1. Now all we have to do is get y by itself. First things first. There's an exponent. That exponent has to go away. We cancel squares with square roots. This is where your algebra skills come in handy. You have to remember that anytime you cancel a square with a square root, you will create a plus or minus on the other side. Now, the square root of 1 is 1. But because I had to take the root of a square, it could have been positive or negative 1. I never would have known. Now we get y by itself simply by subtracting x from both sides. And that'll give us two different equations. Y equals negative x plus 1, and it's not an or statement, it's and. It's both things. Y equals negative x minus 1. Because this is positive 1 and it's negative 1. It's both numbers. When you take this, whenever you take an even root of an even power, it creates this plus or minus. Because this square hides the fact that this number could have been negative and you never would have known. If x plus y equals negative 1 and then you square it, you do get 1. So because we don't know that x plus y was positive, we have to say, well, it could have been positive or it could have been negative. Now, without graphing technology, you should know what kind of graph y equals negative x plus 1 is. It's linear. It's a line with a negative slope. And so is this. But describe these two lines. What relationship do they have? They're parallel. Yeah. They have the same slope. So this is two parallel lines. That is the description of this relation. It's two parallel lines with a slope of -1. I cannot put x squared plus 2xy plus y squared equals 1 on my graphing calculator. But I could put y equals -x plus 1 and y equals -x minus 1 on my graphing calculator. But they are the same graph. This is clearly not a function, because these two lines will fail the vertical line test at every single x value. Neat, huh?
Mm-hmm.
Yay, some people, one person. Okay, now, there are other times when we need to describe graphs using more than one equation. But that doesn't mean they're always non-functions. Sometimes we do it just because the graph is wacky. Like that graph. I made that in Desmos. And look, to the left of my hand, I have a quadratic. I just specifically told Desmos to stop its domain at the number x equals -2. So I told Desmos, graph this quadratic to the left of x equals -2. And then I told it, graph this absolute value equation between x equals -2 and x equals 0. And then I told it, graph this square root equation after x equals 0. This is called a piecewise function, where over different parts of the domain, it has different equations. You should have done it in Algebra 1, and probably Algebra 2. And you saw one in the notes already this year from me as well. You just didn't know it. Right there. To the left of x equals -2, that's a circle centered over here somewhere. Between x equals -2 and x equals +2, it's a straight line, y equals the number 1. And after x equals 2, a circle with the same radius but centered somewhere else. 3 different equations across its domain. So here, I had the piecewise function, f of x is, and this is backwards, I'm sorry it's backwards. You know what? Yeah, we'll just leave it the way it works. I should have typed it like this. And I'm doing it anyway. Should have been -x when x is less than 0 and +x when x is greater than or equal to 0. It's just typed upside down. That peeves me. It should have been done that way. When you do your piecewise equation, your piecewise functions, you really do want the x's to go from left to right. So from -infinity to +infinity. So I just had them upside down. So now that it's in the proper order, we're going to graph this. And then once it's graphed, we're going to say what we see. Okay? Now, both of these things are lines, and they're both in slope-intercept form. Let's do this one. I'll do that one in red. I'm going to graph the line y equals -x. But I'm only going to be able to use the x values that are less than 0. So what is its y-intercept? Well, it doesn't have a plus b, so its y-intercept is 0. And then I have a slope of -1. Normally, you would go down 1, right 1. But you can't go to the right. That says go to the left. So instead of saying down 1, right 1, what I'll say is up 1, left 1. Now, technically, there is an open dot there because there's no equal to bar. However, the blue one is going to be the line y equals +x. And it does exist at x equals 0. So its y-intercept is 0, 0, and its slope is +1, up 1, right 1. But it tells me I can only graph this to the right of the y-axis when the x's are positive. And that then filled the open dot. What did I just graph? What? That is the absolute value of x. So the absolute value of x is a function. So I don't need to define it implicitly. But I can define it piecewise as two different linear equations with restricted domains. Pretty cool, huh? So down here, we're going to use the 12 basic functions to define this piecewise function. In second period, someone asked me which one of these gets the equal to bar when we're doing this ourselves. And the answer is, it doesn't matter, you just pick one, because they meet at the same point. Now, if they didn't meet at the same point, if they had different y values, then the open dot clearly would not get an equal to bar, and a closed dot would. But when they meet at the same point, you just pick one to give the equal to bar to. It doesn't matter. No, you can't give the equal bar to both of them, because that would imply a possibility of getting two different y's at the single x. Okay? Now, to the left of the y-axis, which of my 12 basic functions am I looking at? This is actually not the exponential. Squaring. This is x squared. The exponential goes up and to the right and is asymptotic to the x-axis. It would never touch it. But this one actually does exist at 0, 0. It exists at 1, 1, and it exists at -2, 4. So that is y equals x squared on that side. But on this side, it exists at 0, 0. It exists at 1, 1, and it exists at 4, 2. Which one is that one? Square root. So we go to define this thing then, piecewise. We know we have y equals x squared to the left, and that's specifically when x is, and I like to give the first one the equal to bar when they touch. It's just me, it doesn't matter. So I'm going to say less than or equal to 0. And the other one is just the square root of x when x is greater than 0. So again, I could have put the equal to bar here instead. It wouldn't have mattered because they touch. Now, if they didn't touch, if they looked like, say, this, the open dot would be obvious, and that one would not get the equal to bar. It wouldn't be the same equation. This has been shifted up 1. But my point is, then it would be clear this one didn't get an equal to bar. But when they do come together, it actually doesn't matter which one you give the equal to bar to. Cool? That's it. That's the whole lesson. That's it. It's pretty easy, right? Woo! Good job, nerds.